Hi, my name is Alan Henley. I'm a product manager here at Radiant ZMAX, and I want to thank you for joining our webinar today. Radiant ZMAX is the world leader in color and light measurements, and we have been providing scientific-grade measurement solutions for nearly 20 years. We are pleased to have Leah Selstead, a senior application engineer at Radiant ZMAX, presenting today's webinar called Improving Color Measurement Accuracy for LED, Luminaire, and Flat Panel Displays. This presentation will last about 30 minutes, and after the presentation we will bring our expert panel online to have a question and answer session. At any time during the presentation you are welcome to submit questions or comments through the questions box on the right-hand side of your display. A recording of this presentation will be available on Radiant ZMAX website in about 1 week. And now I'd like to turn this over to Leah. Leah?
Okay, let's go ahead and get started. So this webinar is focused on getting the best possible color accuracy using an imaging colorimeter. The presentation will have several sections. We'll start with Introduction to Light and Color, move on to Introduction to Imaging Colorimetry, and then the need for calibration, like the theory of how this technology works and why we need to calibrate. And then we'll finish off with the Radiant ZMAX solution. So these are custom color calibrations that our ProMetric system offers. ProMetric refers to both our line of imaging colorimeters and the associated software. All right, we'll start with Introduction to Light and Color. So we define light as a very narrow band of the electromagnetic spectrum. The human eye can only see this narrow band from about 380 to 780 nanometers. Longer wavelengths are IR all the way into radio, and shorter wavelengths go into the high energy X-rays, gamma rays, etc. Our interest really only lies in this narrow band because that's what human eyes see and that's what the camera is really intended to measure. So when we are measuring a light source and defining its output, the most comprehensive definition is the spectral power distribution. The spectral power distribution, or SPD, is the light output at a given wavelength. So we'll look at some examples on the next slide, but the idea is different sources, different types of light-emitting devices, it could be LEDs or lasers or fluorescent bulbs or incandescent lamps, for example, those are all going to have different spectral power distributions. All right, here are some examples of common spectral power distributions. And it's important to understand this because it affects the color calibration of our camera. So even though our camera doesn't measure wavelength, or imaging colorimeters don't measure wavelength, they still measure color and they still have to be calibrated. And those calibrations are dependent on the incident spectral power distribution. So in this example, we have some broad spectrum sources like Illuminant D65 in light blue here. So that would be northern sunlight. Or here's Illuminant A, which is like an incandescent light bulb. We also have LCD red, green, and blue components here. Or here's a red LED, so that's a narrower band source. Or we also have this spiky yellow in the background is metal halide. And one of the most important takeaways from this slide is that well, with the exception of the red LED, all of these sources look white to the human eye. Illuminant A and D65 are two different types of white light. The combination of LCD red, green, and blue looks white to our eyes. Metal halide, the spiky yellow spectrum, looks white to our eyes. So our eyes don't see wavelength, they only see color and brightness. So there are three types of cones or photoreceptors in our eyes, and the absorption characteristics of these different photoreceptors account for how we perceive light and color. Light with a particular spectral power distribution will stimulate some cones more than others, and then our brains interpret that as brightness and color. And like I mentioned before, very different spectral power distributions can appear the same. So we need to have a way of defining color as perceived by humans, but in a quantifiable manner. And so in the 20s, some experimenters, Wright and Guild, performed a set of experiments, and what they did was they came up with this mathematical way of defining perceived color. And they came up with these three weighting functions. We call them CIE, X bar, Y bar, and Z bar. CIE is a standards body that keeps these things regulated, and so they review and approve new color spaces and are a standards body so that everyone is on the same page in the world of color measurement. So CIE Tristimulus curves are what these weighting functions are called. There's three of them, and using these, we can define what we call chromaticity. So as opposed to a spectral power distribution, chromaticity does not have wavelength information. It has some format, some type of color coordinates that are used to define the color of a light. So how do we define those chromaticity coordinates using the Tristimulus curves? The way that we do this is the spectral power distribution of a source is multiplied by each of those weighting functions. After that multiplication, each of the three resultant weighted curves is integrated, and those integrated values we call Tristimulus X, Y, and Z. So big X, big Y, and big Z. These three values can be used to calculate chromaticity coordinates in a variety of formats. So for instance, probably the most common is CX and CY, which are these two values here. They're calculated using big X, Y, and Z with these formulas. There are some alternative formats that are just algebraic transformations. For instance, 1960 or 1976, we changed the notation to U and B or U prime B prime. And again, those are just algebraic changes as a different way of defining the color. Here we have the CIE 1931 color space. So this is CX and CY, like we saw on the last slide. And this is, again, this is a way of defining color using coordinates, using two numbers, CX and CY, instead of an entire spectral power distribution. This also takes into account the human vision using those weighting functions. So this is color, a way of defining color as perceived by humans using only two coordinates. So you can see on here is also printed what we call a black body curve or a Planckian locus. This is another way of defining color, and that is correlated color temperature. This is mainly for white sources of different types. So bluer whites have higher color temperatures, and yellowish or reddish shades have lower color temperatures. And these all fall on this curve. And what this curve is a black body radiator at a given temperature has a given color. And so that function can be plotted as such. And then there are some standard illuminants, like we looked at D65 Northern Sunlight as an example spectral power distribution, so that falls right here. Okay, moving on to Introduction to Imaging Colorimetry. And it's really important to understand all this background information so that when we move on to color calibrations, it's comprehensible in terms of why we need to do this and how our calibrations go about improving accuracy. Okay, so for some perspective here, we have instrument technology comparison. There are 3 types of technology listed here, and then the benefits, the relative benefits of each type. So a spot colorimeter is probably the simplest and the cheapest. So it measures a single point, and it measures chromaticity. So like the imaging colorimeter, it does not measure wavelength. So because it measures a single spot, setup time is very fast. It's basically point and shoot. But where we sacrifice is in accuracy and also in the fact that it only measures one spot. All right, so the next type of technology for comparison is a spectroradiometer. A spectroradiometer also measures only one spot, but it has a huge benefit of being the most accurate type of color measurement that we have. A spectroradiometer does measure wavelengths, so it measures the entire spectral power distribution of light. Okay, and then the imaging colorimeter, so the main focus of today, where it excels really is in the spatial resolution. So we don't have the highest accuracy, although with the color calibrations we're going to talk about later, we come extremely close to the accuracy of a spectroradiometer. But where it really excels is in spatial resolution. So you can measure extended sources like displays or uniformity across a luminaire with a single measurement. So that's what this graphic is illustrating. It's showing how different areas of the display are focused onto different pixels of the CCD. Okay, so CCD detector technology is really just a rectangular matrix of photodetectors. An image, or optics form an image on the CCD surface, and then each detector measures incident flux on that pixel. So a CCD does not measure color. It only measures incident flux. And so we have to add some other technology in front of the CCD in order to measure color. And so ProMetric cameras, this is how we measure color, with a moving filter wheel in front of the CCD. So we talked about those CIE Tristimulus curves, the color matching functions. The filters inside the camera are actually matched to those functions. So when light comes through the filter and we measure the incident flux, that's effectively doing the integration. So coming through the filter, the incident spectral power distribution is weighted by the CIE Tristimulus matching function, and then our camera measures those values as big X, big Y, and big Z for each pixel. So this type of filter system provides the best possible CIE match. And again, as I just mentioned, the raw data ends up as CIE X, Y, and Z. And so from there we can calculate the chromaticity coordinates for each pixel. Okay, so let's talk about the need for calibration. So in order to get the very best possible color accuracy, we need the response through each color filter to match the CIE color curves as closely as possible. What that means is that we have to actually account for not only the filter response, but the CCD response. So the silicon CCD has some spectral response characteristic. This is an example for one of our sensors. And the combination of that spectral response of the CCD and the spectral response of the filters has to match the CIE curves as best as possible. And so our filter system does that quite well. For comparison, just for perspective, I have published here a example response for a consumer CCD. So like a point and shoot camera, that you'd go buy at a store for $100 or something, uses a different type of technology. It actually uses a technology called the Bayer pattern, which means that gel is printed on this CCD as shown in this pattern on the left here. And so gel is printed on the CCD in this pattern, and the response, basically the gel acts as the filter. So the response should, in theory, somewhat match the CIE curves. But you can see in this example that it's not nearly as close as our filter-based system is. So that's why something like a consumer camera just really doesn't have any comparable color accuracy. All right, so we've explained how the response of the filters in the CCD matches the CIE curves very well. And in theory, that should mean ProMetric can measure chromaticity directly from each of the 3 filtered images. However, in practice, there are some sources of error that have to be calibrated out. The 3 sources of error are filter error. Sometimes the filters are not perfect. They get very close, but they're man-made objects, and so there is some small amount of error in the filter response. There's also CCD error. Each CCD chip has very slight variance in spectral response. And same with the lens. Each lens has slight variance in spectral response. So we want to calibrate for all of those sources of error. And we can do that all at once with a color brightness calibration. And so Radian ZMax has developed several different types of these color calibrations so that for any type of DUT that you want to measure, we can calibrate and get very accurate color. All of these calibrations are available in our ProMetric software. So that software comes with a ProMetric imaging colorimeter, and the user is able to utilize any of these calibrations as appropriate for your specific DUT. And so now we'll talk about these different calibrations and when each of them are appropriate and the benefits. So again, for perspective, many other imaging colorimeters only provide one calibration. It's relative to illuminant A. And what that means is if the input spectrum of your device is very different from illuminant A, there can be error in measured color and luminance because of the spectral mismatch. Because illuminant, when we calibrate for illuminant A, we're calibrating for that specific spectrum. And so if your DUT has a very different spectrum, it would be ideal to calibrate for that specifically. And that's why we have all these different calibration options, is so that you can have a custom calibration and get the very best accuracy. So the most common type of this custom calibration is called a one color. And this is a calibration for one incident spectrum. So if your device gives off a single color of light, then we can use this one color calibration tool to scale the response through each of the CIE matched filters. The result is a color calibration matrix. So here I have an example of what a color calibration matrix would look like in our software. And you can see that this particular one is for illuminant A. Okay, the next type of custom calibration that we offer is called 4-color. This is one of the most powerful calibrations that we have, and its role is really for RGB displays. So devices that have pixels of red, green, and blue components. So in this case, the way we make the calibration is reference data for each of the primary colors is input, and again we create a correction matrix. So when I say the primary colors, I mean full blue, full red, full green, and then the sum of all of those. So full red, green, and blue to make white. Once we have input data for those primary colors, input reference data, chromaticity can be calculated for any color within that gamut. So for instance, the primary colors would be, here would be the vertices of this triangle. Then once we have reference data for these points, any color within this triangle can be measured, and we can interpolate with using that color matrix, and we can interpolate and make the correction and get accurate color. So here is an example of some data that I took on an LCD monitor. And what I did was I measured red, green, blue, and white with the standard Luminaire calibration that comes with most imaging colorimeters. And then I made a custom calibration. I made a custom 4-color calibration on this monitor, and I remeasured each of those states, red, white, green, and blue. And so what these numbers are is actually the difference in the color coordinate. So when we specify color accuracy, we say, for instance, plus or minus 0.003 CX/CY. So that would mean a change of 0.003 in CX or CY. So I've used that same type of specification here. I have calculated the difference between the measured CX and the reference CX, which I took with a spectrometer. So with the Luminaire calibration, the difference between measured imaging colorimeter data and spectrometer reference is listed here for CX and then CY. And then again, the same metric is listed here with for the 4-color calibrated measurements. And you can see that the difference is significantly smaller. Okay, we have 3 more types of color calibrations that really start to address less common situations. So we want to allow customers to have this accurate calibrated color data for any type of DUT, device under test. So what if your device under test is more than one color, or is not an RGB display, and you still want to calibrate and get this great color accuracy? So we have a few options for those types of situations. The first is called a multicolor calibration, and what this does is create a calibration for a device under test that has many shades of the same color, sort of like LEDs from different bins. So you could have maybe some white LEDs that are a little bit bluish and some that are a little bit yellowish. So in that case, we would use a multicolor calibration, and we would take reference data that covers the whole range of shades. So we would want to use the yellowish one and the bluish one and of those white LEDs. And then we would take reference data with a spectrometer for some sample of those LEDs, input that data, and then ProMetric will create a correction matrix using a least squares method. It will create a compromise calibration that will work for that whole range of shades. Okay, the last 2 types of custom calibrations are really meant to address situations where there are very different colors within one image. So an example for this would be something like a dashboard of a car, and maybe you want to measure the uniformity of the characters, but they're very different colors. Like the turn signal is yellow LED, and the speedometer needle is red, and obviously those are very different, but they don't fall into the existing categories of single color or RGB device, and you don't want to have to take multiple exposures. So in order to be efficient and accurate, we have created a couple calibrations to address such situations. The first is called a multi-area color calibration, and in this case you can define areas of the image for which to apply existing calibrations. So in this case we have existing yellow, green, and red one-color calibrations, and we are going to define areas and tell the software which calibrations to use. Area number 1, we want to apply existing yellow one-color calibration. Area 2, we want to apply existing green one-color calibration. Area 3, we want to apply existing red one-color calibration. So it's pretty simple, just basically applying different color calibrations to different areas of the image. Okay, and our last type of color calibration is very similar to the multi-area that we just talked about, but it's getting a little bit smarter. So in this case, the user selects several different colors on a measurement image and then assigns a color correction matrix to each. So what that means is the user would select this point, for example, and then say for chromaticity coordinates near these values, use the existing yellow one-color calibration. And so what that means is that for every pixel, the software will go through, calculate the chromaticity coordinates, and then say, does this match what the user told me to use a one-color calibration? So for instance, a pixel in this region, the coordinates are going to be very close to what we defined up here. The software will say these coordinates are very close to these ones up here, and for these ones up here we've been told to use a yellow calibration, so we will also use a yellow calibration down here. So it's kind of like the software has got smart. So same thing down here. It would come to this pixel and say the coordinates are very close to what we've defined up here. So the calibration that was chosen up here, we will also use down here. It does this for every pixel within the image and applies the corresponding color correction. All right, a quick review here of the ProMetric color calibration tools. We have a one-color calibration, which is for a specific spectrum coming from a device under test. We have a four-color calibration. This is for RGB devices. We have a multi-color calibration, which is for varying shades of one color. We have a multi-area color calibration, which is where the user selects different regions and applies different calibrations to each region. And finally, we have adaptive select, where the user associates chromaticity values with calibrations, and then the software is able to extrapolate those associations over the whole image. All right, I want to thank everybody for calling in and listening. We have several ways for you to contact us at this point. You can always contact us at sales@radiantzmax.com or alternatively info@radiantzmax.com. You can also type your questions into the space on the right-hand side of your webinar screen. We are going to go ahead and answer some questions at this point. We'll have some question and answer from the audience. So you can go ahead and type your questions in, and we are also going to welcome a few other people from our company to help answer those questions. Alan Henley, a product manager, will join us, and we also have Doug Krazar, our Chief Operating Officer. So we'll welcome them and go ahead and get started with questions.